Assalamu alaikum. The topic of today's video is Hermitian operator. So in this video I am going to describe what is a Hermitian operator. So first of all, you need to consider two functions. One is psi and another is phi, and make it note that these two functions psi and phi are the eigen functions. Okay, eigen functions mean the functions which are repeated after the operator is being applied on them. Okay, so I am repeating this, that psi and phi are two functions and these two functions are eigen functions. Eigen function means when I apply an operator on psi or phi, okay, in the result the same function is going to repeat. That was the definition of eigen function. So I have two functions psi and phi on which an operator A is being applied. Okay, since the eigenfunction says that when an operator, okay, when an operator is applied on a function, okay, when an operator is applied on a function, then we get a constant factor, okay, then we get a constant factor and the same function in the product. Okay, this was the value of eigen functions. This was the equation of eigen functions. So I am saying that I have two functions, one is psi and another phi. So these are two eigen functions. Okay, for example, if I take psi, okay, if I take psi here and apply any operator on it, then I will get a same function in the answer. This was the definition of eigen function. So in this case I have taken two functions, one is psi and another is phi, and I call them the eigen functions, and an operator A is being applied on them. So this operator A, how can this be a Hermitian operator? This operator A can be a Hermitian operator if in case I take integration from negative infinity to positive infinity psi hysteric A operator being applied on phi function d tau volume element. Okay, so the left hand side of the equation says that if my operator is applied on phi, if my operator is applied on phi, then I'll get an answer, and this answer will be equal to the answer if an operator is applied on psi hysteric instead of phi. Okay, on the right hand side of the equation the operator is being applied on psi hysteric, whereas on the left hand side of the equation the operator is being applied on the phi. Okay, so as you can see that both the answer should be equal. So the case in which the answer of the left hand side and the answer of right hand side becomes equal, in this case, only in this case, I can say that the operator A is the Hermitian operator. Okay, I am repeating that operator A when applied on one function, and in the right hand side of the equation the operator A is applied on the second function. Okay, so let's just move on with an example. Let's just see that I am taking operator equal to d square over dx square. Okay, I am taking operator equal to d square over dx square. I have taken psi equal to e raised to power iota x. So what will be the complex conjugate of psi hysteric? The complex conjugate of this psi will be equal to psi hysteric. As you know, in psi hysteric we change the sign of iota. Since iota is positive here, so it will become negative iota. So here I have psi hysteric. The next thing is phi. Phi is equal to sine of x. So these are my two functions, psi and phi. Okay, these are my two functions, psi hysteric and phi, and I am going to put the values of this along with the operator in the equation. So let's just say that I take the left hand side of the equation. So the left hand side, according to the left hand side of the equation, my psi hysteric operator being applied on phi, okay, the region, since I am taking dx, so derivative will be dx. Okay, so now on solving this, putting on the values, I get, in place of psi star I am going to write e minus iota x. Okay, and in place of a I am going to write the derivative d square over dx square, and in place of phi I am going to write sine of x. Okay, so here's the d of x. The next thing I am going to do is break up the derivative, d over dx, d over dx, sine of x, d of x. So the first derivative of sine x, what is the first derivative of sine x? The first derivative of sine x is cos x. So the first derivative becomes cos x. The next thing is dx. Okay, so the next thing that so the derivative of cos x here becomes minus sin x. Okay, d of x. So this minus will go outside. My answer becomes equal to exponential raised to power iota x sin x dx. Okay, so this is my answer that I get when the operator a is being applied on the function phi. Now the operator a is going to be applied on the other function. Okay, since here the operator was applied on the phi, now the operator should be applied on psi hysteric. So now the equation will be just like that. Phi operator being applied on psi hysteric in region d of x gives out. So now I'm going to put on the values. The value of phi is sin of x. The next thing is bracket. In operator, in place of operator, I'm going to write d square over dx square, and in place of psi hysteric, I'll write iota raised to power minus iota x, exponential raised to power iota minus iota x, d of x. Okay. Next thing, sin of x, I'm going to break derivative. In breaking derivative, I get d over dx, d over dx, e raised to power minus iota x, d of x. Okay, so the next thing that you know is when we take the derivative of an exponential, the power comes right behind it. So the first derivative of the equation of this part becomes minus iota e raised to power iota x d of x. Okay, so the next thing that I'm going to do is to take the second derivative. When I take the second derivative, what will be the answer? The second derivative says that this minus iota will come again behind. Minus iota into minus iota e minus iota x d of x. Okay, the next thing says, as you know that minus minus becomes plus, and iota square has a value equal to minus 1. Minus minus become plus, and I write iota square here, e raised to power minus iota x d of x. So next thing is, as you can see that iota square has a value of minus 1 e raised to power minus ix dx. So this minus will go behind. The answer becomes equal to e minus iota x sine of x dx. Since this answer here, okay, this answer here is equal to this answer, so I can say that my operator here is a Hermitian operator. Okay, since the left hand side of the equation become equal to the right hand side of the equation, so I can say that the operator that I have used here is a Hermitian operator. So as you can see, even after applying the operator on the phi, okay, in the left hand side of the equation the operator was being applied on phi. Even after applying the operator on phi, I get sine x in the result. Okay, what was the value of phi? The phi had a value of sine of x. Okay, the phi here I took the value of phi equal to be sine of x, and after applying the operator on phi, I get same sine of x in the result. So I can say that this phi here is an eigen function because it is repeated in the result. And similarly, if I talk about psi hysteric, the operator was being applied on psi hysteric here. So what was the value of psi hysteric? The psi hysteric had a value of e exponential raised to power minus iota x. Okay, psi hysteric had a value of exponential raised to power minus iota x. Okay. So when the operator a was applied on this, this value here, I get the same value in the result. Okay, since the value of the function repeated in the result, the same function was repeated in the result, so I can say that this psi hysteric is also an eigen function. Talking about overall, the answer of the left hand side of the equation becomes equal to the right hand side of the equation. So I can say that this operator here that I have used, this operator here is a Hermitian operator. Okay, so this was all for today's lecture. Inshallah, see you in the next video.